recording. Nice. All right. I just, as an addition to, like, I don't care if it's Python or not, Colab, that was for 161. Put that there. This is PyCharm. Can you all see that reasonably well? Let me turn off all the lights. The lighting is obnoxious with that. Is that reasonably visible? I could probably turn the font up later if that helps more, but we'll worry on that later. Here, let me have a quick look. See if we can find real quick. See, this is a newer version of PyCharm. They've even like moved things around. Editor, probably under editor. Font. Size. Let's try 15. Is that better? Can't really tell. Worse somehow. Let's stick with this for a while and see if you want it bigger. All right. So yeah, I'll probably be doing a bunch of stuff in PyCharm just because I'm used to it. If you like VS Code, go for it. If you like to program in an interpreter or a notepad, by all means, have at it. But I'm using PyCharm. All of this, like I said, you can clone the Git repository and pull all of this code yourself and whatnot. But today's topic, we are going to jump weeks ahead and just implement a genetic algorithm, okay? I could talk at you about all the theory and all the ideas behind it, which we are going to do, but I think it'd be kind of good to just implement a genetic algorithm, a GA, implement a genetic algorithm. We'll talk about the things as we go, and then after having implemented one, a lot of those gaps will get filled in. By all means, if you have questions as we're going, ask. Happy to answer them. But, I lost my train of thought. Yeah, happy to answer them, but be aware that, yeah, I'm going to go into more conversation about, okay, population, et cetera, after. So implementing a genetic algorithm. The purpose of this is to just see a very simple GA. Now, I'm using the word simple GA. Simple doesn't mean trivial. Simple doesn't mean not capable. I mean, it's going to be like a very basic, bare bones. This is like, at the very least, what you got for genetic algorithm. It's got no bells and whistles. It's just a very basic genetic algorithm. It includes all of the parts a GA needs in order to be a GA. And despite never seeing a GA before or knowing the intuition behind any of the ideas, I think this topic is going to be very manageable. But you'll let me know at the end of this topic to see, let me know if you followed it or not. After this topic, after this one that we're going to go through, I don't know if we'll finish it today or even this week. I don't know. We'll take our time. The next topic is you all sitting down and implementing it and tinkering with it and playing with it and seeing what you can do and just answering some questions together or on your own, whatever. So we will do that in lecture as if it's kind of like a lab. So not only are we going to learn it and implement it here, but you're also going to have a chance to sink your teeth into it and get your hands dirty, okay? I think it's the best way to learn this stuff. Okay. Before anything, we're going to have a problem we want to solve with the GA. Now, when I use the word solve, I got to be careful in what I mean by solve. A lot of times you'll even see me, I don't have it here. I italicize solved because, like, well, to me, solved seems as if, like, I found the best solution, right? But the problem is, in general, when using a GA, you're using it on a very difficult problem where you kind of go like, screw it, I don't know, let's throw a GA at it and hope for the best. And a lot of those problems, we're not going to find the best solution there is. We're going to find a solution that's good. Like that traveling salesperson problem, the TSP, that one I talked about last time. If you've got 100 cities, now this is not a joke. If you have 100 cities and you want to find the best path to visit all those cities, there are more possible routes than there are particles in the universe. FYI. That's a big number. So if I say, I want to find the best route, you're having a laugh. No, you're not. You just need to find something that's good. And if one day someone shows up with something better, even better. But I just need something good. Because it's also not navel-gazing in the sense I want to find, some people do this when they're implementing algorithms and they just kind of want to get better and better results. I found the best path on this particular instance of TSP. Hey, aren't I amazing? Yeah, some people do that when they're testing algorithms and trying to do enhancements and whatnot to try to find good solutions. But remember, the point of these algorithms isn't to navel-gaze like that. It's to actually solve problems. So if I'm some delivery agency and I need to visit 100 places, I need a good solution. And if it's good, I'm happy. But it's also a little bit more interesting than just like finding a good solution, because to me, there's kind of an open question on, like, with certain problems, does there even exist a best solution? All of you know how to walk, right? I've seen you walk. I can walk. I'm walking. In your brain, there is some configuration of stuff in your brain that enables me to walk. Just like there's one in your brain, in your brain, in your brain, in your brain, in yours, and yours, and yours, and yours. It's all there. But do you really think the configuration in mine is the exact same as yours? Probably not. Our brains aren't even the same shape or size. Brains are weird like that. Meaning, I've got some encoding for walking, some program. So do you, so do you, so do you, so do you, so do you. Do you think there exists a best possible configuration for walking? Do you think there's such thing as, like, that is the best walker in the world? Maybe? I don't know. It seems kind of like a stupid thing to think about. Maybe there are some problems out there where there really is no such thing as the best solution. Maybe sometimes it really is just there are good solutions. Who here has been walking for most of their life? Who here has maybe ever tripped every once in a while? Yeah, I kind of, right? Maybe you kind of actually suck at walking. I don't know. But the point is, it gets you through the day. And if you think this is a silly example, I think it's pretty good, actually. I think it's an example that shows maybe there are some problems out there where there really is no such thing as the best solution, and we just kind of hope for the best. Now, the problem I'm about to introduce is stupidly simple. People will call something like TSP a toy problem, not because it's uninteresting, but because it's a good problem to play around with when working with these algorithms, because it's well understood, and we can kind of get a sense of how changes in the algorithm affect the solutions to the problem, because everything's well understood. Using a GA to learn to walk, well, that's not really a toy problem at all. That's pretty tricky. I don't even know what that would be. The problem I'm about to introduce isn't even a toy problem. It's a stupidly easy problem. You would not use a GA for this ever. But the reason we're using it is it's well understood. You all will understand this problem really quickly. You know what the best solution is. You know what incremental improvements are to a solution. And you know what the worst solution is. You will know everything about this problem. The point of using this problem is to see the GA at it. Okay? Now, this amazing problem is going to be maximize the integer value of an unsigned binary string. So if I said, I've got 8 bits, and I want to make a GA maximize the value of that binary number, what's the right solution? It's not a trick question. A bunch of ones, obviously. A solution with a bunch of ones, but 1 0 isn't as good as one with more ones, right? Yeah. A bunch of zeros, that's really bad. So you understand this problem. It's a stupidly simple problem that I am aware of. The point is, we're playing with it for the sake of learning. Okay. The problem Maximize the integer value of an unsigned binary number. Find the largest binary number representable with n bits, where n is some arbitrary number of bits. Obviously, as we make n bigger, the problem becomes a little bit harder, right? Instead of having to find 10 ones, we got to find 11 because n was a little bigger. So that's the situation. For this problem, the search space, remember yesterday I was talking about the search space being that like the highest and lowest parts in this room, right? So the search space is like the 2D plane that is the surface of the floor, looking for the lowest part. That was the search space. Here, the search space is the space of all possible unsigned binary numbers of length n. Okay? They exist in some space. And we want our algorithm to search through that space to find the one that's the best. Just like when we had the floor, imagine having an algorithm. Imagine a little robot rolling around on the ground looking for the lowest point in this room, right? How is that robot going to try to find that room? Or to find the lowest spot, right? It's going to have some trick to try to maybe find it quickly. I don't know. I mean, there is a simple solution to that problem if I wanted to find the lowest point in this room. I could just have it go and explore literally every point in this room. Fine, yeah, good. But with some problems, taking that strategy might be intractable, which is a fancy word to say it ain't happening. For example, best route of 100 cities. Yeah, the algorithm's simple. Try every possible route and pick the one with the smallest path. Great. It'll take you longer than the universe has existed by 1 billion times. That ain't happening. So that's where these algorithms show up, when the problems get more difficult. Again, this problem ain't too difficult, but it's for learning purposes. So given the problem description, the best solution is obviously a string of n ones. Obviously. So consider an example with n equals 10. How would these candidate solutions be ranked in terms of their goodness? Well, I already kind of ranked them for you, right? Which of these is the best? This one or this one, right? Is this one better than this one? Yeah. See, there you go. Why? And I even gave you the integer values over here, if you didn't notice, to make it a little easier for us to understand which is better. So the GA being written will evolve these bit strings with the goal of maximizing the integer value of this unsigned binary number. Okay, that's the goal. Like I was saying, one would not realistically use a GA to solve this problem. It's a stupid problem, but we're using it. Yeah. So, initialization. Remember when we looked at that image yesterday, there was initialization, evaluation, selection, variation, and that would loop. And then eventually we got to stop. That's what we got to do. So where better to start than initialization? So before evolution can begin, we need an initial population of candidate solutions. Population is the collection of candidate solutions. A candidate solution would be like one. In this particular example, a candidate solution is a potential solution to the problem. That would be like some arbitrary string of n bits. That would be a candidate solution. And we have a population of them. We have a collection of candidate solutions. How big that population should be, entirely up to you. Should it be 10? Should it be 100? Should it be 1 billion? Whatever. The answer to that question is whatever works. So there we go. Okay, we need to make a population of candidate solutions, and a single candidate solution is a potential solution to the problem. So for example, 10110010001 is a valid candidate solution for finding the largest binary value when n equals 10. So far, so good? It looks like you're like,
I was confused about n.
n is just some arbitrary, that's the length of the bit string. Told you it's not too bad, right? We're following along. That's what we got to do. Now, like I was saying, we need to know how good these are. But in order to computationally evaluate how good they are, Now, in this particular example, it might be trivial how we are going to encode those candidate solutions. A candidate solution is a potential solution to the problem. But how are we going to encode that in our algorithm? How are we going to actually represent it? Here, it's fairly straightforward. But sometimes it's non-trivial. Sometimes it's a little trickier. And we're going to see examples of where it starts to get a little bit complex. But with this particular example, I think a good encoding is going to be, I don't know, maybe we could do like literally a string of zeros and ones, maybe a list of zeros and ones. Some linear collection of zeros and ones would be suitable for an encoding of a bit string. Would you agree? It's fairly obvious, right? Because this is what we would call a very direct representation. Because what a candidate solution means and how it's encoded are very similar. It means a bit string. And we're encoding it as like a bit string, right? But sometimes we've got complex problems that we have to encode very cleverly. And we'll see many examples of those. An encoded candidate solution is called a chromosome. You will notice throughout this course, the computer scientist really worked really hard to steal biology words, but it's just an encoded candidate solution. All right, so a chromosome is a candidate solution. Often people, including myself, I might do it in this course. I'm going to try not to, but I probably will. I might mix them up. I go to academic conferences where people talk about this all the time, and everyone's mixing it up just because everyone knows what it is by the context, so be aware that I might do it too. All chromosomes are candidate solutions themselves, right? It's an encoded candidate solution. So just be aware that sometimes I might mix and match these words, but to be as precise as possible, candidate solution is a potential solution to a problem, and a chromosome is an encoded candidate solution. But all chromosomes are candidate solutions themselves, right? I might even be like overcomplicating this. So if you're left going like, what? Ignore it. You're fine. So for the integer maximization of an unsigned binary number, there are some obvious reasonable ones. Here, a list of zeros and ones will be used. Why? Because I think it's easy. Thus, the candidate solution 101100101 can be encoded as the chromosome, that's a list, 1, 0, 1, 1, 0. You get the idea, right? A single chromosome we can very easily create by just randomly generating a string of zeros and ones. Okay? And that's how we're going to do our initialization. So the idea will be, I'm going to create some number of candidate solutions, chromosomes, by randomly generating lists of length n of zeros and ones. That's what I'm going to do. That's the idea. So if I wanted a population of size 100, meaning I wanted 100 candidate solutions in my population that will evolve together, if I have a population of 100 and I'm evolving bit strings of length 10, I will generate 100 lists of randomly generated zeros and ones of length 10. Yeah? Yeah, that's all. If it seems like, I'm following it. If you were thinking like, why is he hitting these points so hard? Obviously, I'm following. It's because I'm really actually trying to emphasize how simple this is. Evolutionary computation at the basics is relatively simple. And right now we're at the basics. We're in good shape. So a single chromosome generated randomly zeros and ones, for example, used here the length was n, right? So yeah, there we go. Yeah? Any questions? Any at all? Nothing. It is just that easy, or you are so lost that you don't know anything. Raise your hand if you're like, yeah, I get it. Hurry up. Move on. Okay, most of you. And you're just being nice, I think. Okay, a population is just a collection of candidate solutions. How many? It's up to you. Population could be created by creating a list of randomly generated chromosomes, like in the example, a single chromosome, list of zeros and ones, like that. So a population is like a list of lists of zeros and ones in this particular example. It doesn't need to be a list. It could be some other linear collection. But for simplicity, just a list. So we've got the inside list. Each one of these is a candidate solution, a chromosome more specifically. And then it's bound in that bigger list. That's the whole population. Right? So far, so good. Each chromosome is randomly generated. Below is an example of how one could generate this really easily. So here's some Python code. Raise your hand if you have Python experience. Really high, I want to see. Okay, everybody, good. Okay, cool. If you've got a lot, great. If you've got a little, you're going to be fine. Python tends to be fairly straightforward. The only thing in here that might throw you off is the choices function that I'm using. But let's work through this just to make sure everyone is on the same page. We start with an empty list. That's the population. Empty list because there's nothing in it. Then what I do is, for population size, that is some like global constant I set that I just set before everything. That's like one of my, people call these hyperparameters now. It's a setting for the algorithm before I hit run. So this could be 100, a billion, a trillion, whatever. It could be whatever you want. Empty population, create a chromosome, choices. Right here, this is just a built-in function from the random library in Python. So it would be random.choices, where it says from this collection, which is just 0 and 1, so from zeros and ones, create a randomly generated thing of this length, where bit string length is another thing I set. So in this example, if I had a population of 100, population size would have been set to 100, and k would have been set to what n was, which was 10. Yes?
I don't know if that's an underscore in range. Does that,
Here?
yeah, the start, does that like forego the need for
Exactly.
for loop plus 1?
Yeah.
Yeah.
It forgoes the need for having, I could have put an I here, but I wouldn't be using the I anywhere. So the underscore means just loop this many times. I don't give a shit. You don't need the I variable. Yeah, good catch
Does
though.
that count as 0 in the if you do the 4 in range?
Yeah, it starts at 0 to whatever this is, but not inclusive. Yeah, 0 to 99.
Yeah, okay.
Yep. So yeah, and so the underscore, for those of you that are unfamiliar, in Python, if you ever have something that like returns a value, and you really just kind of want to ignore that value, you don't want to put it anywhere, you just throw an underscore in there, it'll do the trick. So here's an example of how it's done. Also, if you have like a function that returns a tuple and you really don't give a shit about some of the values in the tuple, you could just add underscores. And if you don't know what I'm talking about, it doesn't matter. That's a Python thing. Pythonisms. Okay, so there we go. There. After I run this, that's initialization. Those 1, 2, 3, 4 lines of code is initialization. If I wanted to get fancy, I could have even done it in 3. I just felt like making chromosome its own thing because I think it makes the code a little bit more readable. For those of you that know me, what do I consider good code? I don't know if you've... Who here's had me before as a prof? 1, 2, 3, 4, 5. Okay, yeah. So for those of you that have had me, I mean, it might have been a while for some of you, though. But what do I consider good code?
Variables make sense.
Pardon?
Variables make sense.
And you said readable? Yeah. Readable. If your code is more verbose, but I can look at it and immediately go like, yeah, I got it. If your code is nice and tight and I'm reading it, I'm going like, what the fuck are you doing? That's bad code, all right? So make it as nice and verbose and readable as you can. It's nice, it's good. So there, initialization. Any questions about that? Now, if this was a problem, let's say, for whatever reason, I don't actually understand that the best solution is all ones. But I know for whatever reason, on this very difficult problem I'm trying to solve, I've got some intuition about what a good solution might be for this very difficult problem of mine. And my intuition is, it seems as if more ones is better, right? But I don't really know. And I still want there to be like diversity in my population, meaning they're not all the same. I want things to be a little different. Maybe what I'll do is I might bias my initialization a certain way. If I know something about the problem, like with TSP, your typical way of initializing a GA for TSP is to generate random permutations of cities to visit. That's what you do. But if I already know a couple of pretty good solutions, maybe I include those in the population as well. I seed the population with something I know that's already good. You got to be careful. I don't want to bias the search to find local optima, a local optimum, right? But I can seed it a little bit. So here I could seed it with maybe some candidate solutions that have more ones than zeros because I've just got this idea. But I don't really know. I could do that. But here, purely randomly generated. One of the common themes in this course is, aside from the basics, aside of the high level idea, sky's the limit. What's the best way to do initialization? Doesn't fucking matter. Do whatever you want. What's the best way to do that? Literally whatever you want. The more creative and interesting your solution is, I'm fascinated. That's good. That's a good thing. There's no right way. There's wrong ways, but there's no like correct way with any of this stuff. But that's part of what makes it so interesting to me. And what else is interesting is it just works. It's crazy. And another good thing about evolutionary computation is it tends to get really good solutions where I don't need to know anything about the problem. I could know hardly anything about the problem, throw a GA at it, and I get good solutions. Huzzah. I could probably even maybe find a better solution if I spent time studying and making a custom-made algorithm for this particular problem. Maybe I could have, but then I'd have to learn something. I don't want to learn anything. I just want to throw GA at it and hope for the best. That's another benefit of these things. Okay, the number of chromosomes within the population is defined by some hyperparameter called population size. The number of bits in the binary number n is called bit string length. Why? Because that's what I called it. They have no other meaning other than what I just made right there. I will note, just as a warning, who's here heard the word hyperparameter before? No? One person? Okay. So, two people. Okay, actually, so I could have done it the right way. So, classically speaking, hyperparameter is a terrible word to use in this context. So for the longest time, for decades, these were just tunable parameters. These were effectively, they were settings that you could, they were knobs that you could turn before you hit run on your algorithm that would affect how the algorithm runs. So maybe I just turn population size up. Maybe I turn something down, something that I hit run, get a result. Maybe I change it a little bit, hit run again, see how it affected the result. You're going to be doing this with the next topic, tuning those parameters. We call them tunable parameters. But the problem was, or the problem arose when deep learning really took off, because they called those things. Who here knows a little bit about neural networks? Deep learning. Okay. Long story short, you've got these crazy networks, and in the nodes you've got these like activation functions, and in the edges you've got these weights, right? And the weights are what's updated as it learns. The weights change. This is very simply speaking. Those are called parameters, okay? And that's like taken from like statistics, because like in a regression analysis, you find parameters. The mathematics help you find the parameters for, so they use the word parameters. But then they had a problem because they're like, well, we also have those big knobs that we were calling parameters that we could turn before we hit run. So they were using parameters for two different things. Parameters for what's being learned while the algorithm is running, and parameters for how they were setting the knobs before they hit run. So they decided to start using the word hyperparameter, which has an entirely different meaning, but that's what they started calling it. And for the longest time, everyone else in the machine learning community were like grumbling, going like, oh my God, hyperparameter. But then eventually everyone's just like, screw it, fine, they're called hyperparameters now. So just hyperparameter is a word I'm using to mean tunable parameter, one of the dials you can set before you hit run. You'll hear it in deep learning all the time. All right, so there we go. Now, evaluation. So we've got our initialization set up, and if we go back to that image, you've got initialization, it goes down to evaluation, selection, variation, evaluation, selection, variation, and that just loops forever until you decide you want to quit, and then you terminate. So the next step really is evaluation. So after generating the population, the candidate solutions they're probably not going to be particularly good, right? I just randomly generated a string of zeros and ones. They're not going to be great, right? The goal is to find the biggest unsigned integer value. So even though they're all going to be garbage, some will be better than others, but I got to know. So I need a way to actually, I need a mechanism to actually measure how good they are. And for that, we call it fitness. Fitness is another word that they took from the biologists that has a slightly different meaning. Fitness usually means like ability to survive and like have children. It kind of still does fit here in the context of evolutionary algorithms, but we took the word fitness. So fitness is the goodness of a candidate solution of a chromosome. Okay? Okay, the mechanism to calculate this is called a fitness function. And below is an example fitness function for this problem. So let's go have a look at it. I called it value fitness, calculate the decimal value of the chromosome, and here we go. This, I will admit, has a lot of Pythonisms, and maybe I should actually change it because I don't really like the amount of Pythonisms. But all this does is turns that list of zeros and ones into what its integer value is. That's all this code does. If we really want to get fancy, okay, it can raise an exception if the chromosome it gets is length 0, whatever. What is it actually doing? Well, for each bit in the chromosome, turn the bit into a string, and then basically append it to this string that starts as an empty string. So it first turns the list of zeros and ones into a string, like an actual string of zeros and ones. And then it converts that to an integer from base 2. If this is what's confusing you, it doesn't matter. All that matters is this is the fitness function that tells me what that string, what that chromosome of zeros and ones actually is as an integer value. If you wanted to code it differently, I encourage you to do so. I even find this complicated. But it was the easiest way to do it instead of getting all fancy with math. So there you go. Any questions about this fitness function? It's a good fitness function, right? The goal is to maximize the number, the unsigned binary, find the biggest integer. Well, you should probably actually know what that binary string is as an integer. The bigger the better, right? That's what we want, right? Yeah? So with the fitness function, the fitness of each candidate solution with the population could very easily just be calculated with literally this loop. All right? That's it. I want to emphasize again, if you're like, this code looks like it could be out of 161. Yep. It is simple. It's nice. It's clean. It's simple. Here, I created another list called population fitness that will store the fitness values of each chromosome with the indices like match. So the chromosome at index I in the population, its fitness value will be at population fitness index I, right? If you really want, and you want to get fancier, where you create a class called chromosome that stores both the actual encoding and its respective fitness value, by all means go ahead. I just think it's simple to have two separate lists. That's all. But I could have made it more sophisticated if I wanted. I just kept it simple. So for each chromosome in the population, calculate the fitness and then append that to the population fitness. That's all. Any questions about that? I know, it's so nice and simple, right? Right? Now, selection. This kind of actually, you were asking a question about this the other day, yesterday, about, well, do you always just pick the best? And well, there's reasons for it that we will go into a little bit more as we go through the course. But the general idea is more fit, better, candidate solutions should be more likely to persist within the population. But there's no guarantee. So the probability of candidate solutions with a higher fitness value, or I shouldn't say higher, I should say better fitness value, because sometimes we have minimization problems and sometimes we have maximization problems. So the candidate solutions with a better fitness value should have a higher probability of being selected. Those with a low fitness should still have a chance of being selected, though, because chances are, we don't really know, there's no guarantees on any of this, but in general, if you have a candidate solution with a very high fitness value and one with a very low fitness value, chances are, at the very least, they're probably quite different, right? And differences are good. Diversity in that population is a good thing. And here's where it actually starts to get kind of interesting. And it's going to be hard to communicate this because you don't have a lot of experience with evolutionary computation yet. But the fitness measure is only one possible metric of a candidate solution. Hold on, how do I word this? This is a tricky one. The fitness is what I decided was good for that candidate solution, right? But that was me. And that's based on what I think is good. And there's also this ever-competing thing in evolutionary computation on what's good for an individual versus what's good for the population. They might not be the same thing. For example, if you go straight on fitness, which is what I decided was good based on what I think is like the optimum result, what's actually good, what's actually truly good for the evolutionary algorithm is actually not the fitness value. It's all of the mechanisms at play in the evolutionary algorithm. I know you're like, what the? Once we get through this, it's going to start making more sense, but I will say that you really only get an intuition of this, get more experience with it. I set the fitness value, meaning this is what I want. But what I want isn't necessarily the thing that's best at guiding the evolutionary search. It's one of the things that guides the evolutionary search. Diversity is insanely important for your candidate solutions. And we will see why with an example at the end of this topic. But even though something with a low fitness, that was my arbitrary measurement. That was designed, don't get me wrong. But diversity, differentness in the population is immensely valuable. And that is a mechanism I'm not explicitly measuring. Some people do. It's called like novelty search, and there's mechanisms to increase diversity people go with. But I'm not explicitly going to be measuring diversity, but I'm going to be using selection in such a way that it emphasizes diversity. So even though it's not something I'm explicitly measuring, it's something I'm actually encouraging in the population because that is immensely good for the search as a whole. Anyways, it's pretty cool. You'll see it as we go. Okay, selection. All right, less fit candidate solution should be more likely to die off. However, it's not as simple as always selecting the best candidate solution. Yeah? Yeah.
Can I ask what the 2 at the end of
Ah.
the term there
Right here?
does? Yeah.
That's for the int. It turns the list of zeros and ones into a string of zeros and ones. That's this bit.
Okay.
And then it converts that string of zeros and ones into an integer of base 2.
Oh,
So like the string, it's like
okay.
convert the string, which is a base 2 number, into like a decimal. That's what it means.
Thank you so much.
It is kind of a funny one, yeah. All right, so it is not as simple as always selecting the best candidate solutions. Doing so would cause a population to converge too quickly, and it gets stuck. Think of something in like real life. Imagine a population somehow really fit candidates. So there's this example like Neil deGrasse Tyson gives of like these little like worms. I'm not going to get it right, but I'm going to try my best. These little worms were like somehow through evolution they learned in water they got to swim up, right? Because of like oxygen levels or something. Do not quote me on any of this. I'm not going to get it right, right? They learned to swim up because of oxygen levels. They liked the oxygen levels. But as they moved environments, and some of these worms would like swim down, and it wasn't really good for them, but it wasn't bad enough that they died off. But over time, they got better and better at swimming up for the oxygen levels. Then something happened where the oxygen levels in the water changed significantly, where somehow the balance of where it was changed, and those that were all swimming up died off. Something in the environment changed such that what was good wasn't anymore. Because it's the environment that really is what's dictating the search. The environment being all the constraints that we set on it. Yeah, suboptimal solutions. Okay, this is where it becomes important to think about the population, not individual candidate solutions. And this is another interesting thing. When we are evolving, like, look, we're looking for the best candidate solution in the end. I want the best solution. But we're not evolving candidate solutions. We are, but we're evolving a population. That's really what's getting done here. So the fitness function is a metric for the ultimate goal, finding a candidate solution that best solves the problem. But through the process of evolution, we need more than just the ultimate goal guiding it. This is like where diversity comes in. This can be done in many ways. There are no hard rules on how this should get done. No hard rules on how to emphasize diversity. No hard rules on how you do selection. But a very popular, very simple one is something called tournament selection. And I'm going to use it here. Here's what you do. You randomly select a subset of the population. Maybe I say pick 3 candidate solutions from this 100. Of those 3, one of them's probably going to have the best fitness. Maybe there's ties, then whatever, flip a coin. But one of them will be better than the others. That one gets selected. Meaning it's possible, of that 100, it's possible of those 3 I picked the best one, the second best one, and the third best one. And so the one that gets picked overall would be the best one of the whole population. But it's also possible that I picked the 3 worst candidate solutions, meaning the best of the worst still gets to go to the next generation. So this is the selection strategy we're going to use, tournament selection. It's very simple. It works. So randomly select a subset, select the best of the subset, and you repeat this process until we've got the whole new population. Because if I have 100, if my population is 100, I want to fill a new population for the next generation. This is where that loop is. Evaluate, select, variation. Evaluate, select, variation. If I pick 3 and take the best one, I only have 1. I need to do it 99 more times before I, select for the next population, right? So I repeat this process. So here's tournament selection. I've got a couple parameters here. Population, population fitness, selected indices, and direction. Direction, I'll explain in a moment. Direction is just, it'll either be positive one or negative one, depending on am I maximizing or minimizing, meaning there are some problems where I want a higher fitness, for example, maximizing the integer. There might be some where I want to minimize, for example, minimize the distance for TSP. So the direction is a way to say I want bigger is better or smaller is better, FYI. That's why it's set as 1 as default. You get bigger. So just a couple of exceptions, whatever. So max value, you'll notice that multiplied by direction, that's just for the minimizing or maximizing. This right here, it's just a linear search. Do a linear search through the selected candidate solutions and return the one with the max index. That's it. That's all it is, right? So from the population fitness, take the selected indices at index 0. Its index is whatever index 0 is. For index in the selected indices, check it. This obviously compares 0 to 0 once because I'm too lazy to code it, so it doesn't. And it's just a linear search. If its fitness is better, look at each of the values at the selected indices. If its fitness is better, that's the one you're going to want to return. And remember, it's just a linear search. That's all. So this tournament selection only returns a single chromosome, so you must run it multiple times. So here, what I've done is I've created a new list called a mating pool. For population size, randomly select the indices, right? So if I want to randomly select 3 indices, okay? 1, 2, 3. Pick 3 indices from 0 to whatever the population size is, yeah? It's possible, this one with choices, it could pick the same index twice, whatever, it doesn't matter. It could pick it 3 times, however, whatever k is, it's possible, but we'll just ignore that. So just randomly pick 3 or k indices, apply tournament selection on those indices that you selected to find the best one, and add it to the mating pool. And do this for each spot in the population. Any questions on this one? If what's throwing you off is choices, because I'm seeing some kind of like blank stares, all it is this is a list of 0 to population size, 0 to population size minus 1. So if population size is 100, this will select k things from this list. So 0 to 99. K is the tournament size. How many things am I picking to pick the best one of? So those are the indices I selected, and then I give it to the tournament selection function, which is over here, and it returns the best of those that were selected, and we add it, and I just repeat until the population is full. The above pool, I call it the mating pool, ultimately becomes the next generation. It's just mating pool for now. The size of the tournament is defined by the hyperparameter tournament size, and this is what we'll end for now, unless there are any last questions. Okie dokie. See you later.